Week in Science and Education, episode 84. I'm Nicole Tate-Hill, filling in for Kevin Kugler. As always, I'm joined by our co-host Thomas Merritt from Lurton University and Colin Jago from the Kawartha Pine Ridge District School Board. And our guest today is Dr. April James. She's up at Nipissing, and she's going to tell us all about freshwater sustainability today. So, April, why don't you tell us a little bit about your research?
Okay, well, I am a hydrologist by training, so I really study, or a watershed hydrologist, so I study how water moves through our watersheds into the aquatic environment. So a lot of what I study are those processes by which water moves, how it infiltrates the subsurface, how it moves towards streams, headwater streams, for instance. Of course, up here in northern Ontario, you have a lot of lakes, a lot of wetland systems, so how water moves into those systems. So you could call me a terrestrial hydrologist in that respect. I have some background also in hydrogeology, so that idea of groundwater being connected to surface water. In some instances, groundwater will be moving water into the streams, into the lakes. In some instances, you might be losing water from those water bodies into the subsurface, recharging groundwater. And so we look at those kind of processes as well. All these natural processes that we study are relevant to freshwater sustainability in that we can talk about the quantity of water. What happens when a big rainstorm comes along? What are the flow paths of water? And if water's flowing through different parts of our landscape, what are they bringing with it? It could be natural nutrients or nutrients from the landscape. It could be contaminants. And so that's where we can kind of think about terrestrial hydrology linking in with freshwater environments.
Okay, thanks for that, April. That was a really cool introduction. I'm sitting here thinking of like from a high school point of view, and actually from my point of view, can you give me an indication of how you study underwater ground flow? Because when it's on the surface, you can see it going places, and I have limited understanding, but I just want to know how you go about studying flow and how it changes from one spot to another when you can't see it and everything is underground. Can you give us an idea of how that works?
Yeah, sure. No, that's a really great question. It really is, in some instances, the bane of our existence, right? How do you study subsurface movement of water? So there's a few ways we can do it. Ultimately, some of these techniques that we can use, so we can use field techniques. We can go out and we can physically try to measure it, and I'll talk a little bit about those. And then there's other techniques as well, but let me focus on those. So we could go out and we could put in, for instance, groundwater wells. A lot of the research that we do has historically been done on what we call experimental catchments or experimental watersheds. So these are research groups or sites here in Canada, and I've seen there's really wonderful examples in the United States as well, where they've studied these processes in detail by putting in a lot of instruments in the field. This would include shallow groundwater wells, weirs in streams, and those are essentially a location where you get to measure the amount of stream discharge, how much water is flowing per unit time, volume per unit time coming out of a headwater stream. One of these experimental sites that is really well known here in Ontario is the Dorset Environmental Science Centre, which is just an hour and a half south of here in North Bay. And the Ministry of Environment has been monitoring these a suite of experimental watersheds or catchments, headwater systems. So these are really quite small. This is where streams kind of begin using all sorts of this kind of instrumentation, these shallow wells, what we call piezometers. And they measure the pressure in the subsurface. We measure what's coming out in the streams. These are some of the instruments. We might have we'd have weather stations there. We'd measure how much rainfall was occurring. So if you think about what happens when it rains, how do those streams generate water? That would be important to measure the inputs, including rainfall, solar radiation, temperature, what happens if the ground freezes and it rains on it versus what happens if, we're in the middle of summer and it's really dry. Sure. Those kind of conditions are all very important to us.
Maybe I could follow up on that with a question about time frame. So, I mean, I'm also in Northern Ontario, so we're just about an hour apart. And Lake Ramsey, where I row and that I can see from the end of my hallway here, is relatively low at the moment. A lot of water is relatively low. When you're looking at these questions, you know, it's either raining or snowing right now. Apparently it was snowing a couple of minutes ago. Now it's like it's raining. There are times where Northern Ontario is a challenge. Is this a quick process? So are we looking at this rainwater making it into this catchment today, this week? I assume that varies by catchment. So how do you define a time frame for your research?
Oh, that's also a really good question. So, for instance, I've done research that have been, bright scientists and teachers. I've focused. Some people focus on a time scale of a rainstorm, you know, which could happen over hours, right? And you could do super detailed analysis and say, is this an average storm? Is this representative of typically what happens on the landscape? How does that fit into the larger, you know, kind of normal behavior? And then we might also, at these experimental catchments, think we would have a 30 plus 60-year record maybe in some instances of what's been happening over really quite extensive periods of time. So we could put those individual, you know, kind of detailed studies into a much larger timescale study. So we do all of the above, but it's true that in many instances you have to design your experiment from, you know, in terms of what are your research questions and what are you looking for specifically. Then, you know, you might design your experiment to a specific time frame.
So my question is, you know, maybe I'll represent Southern Ontario for a minute here. You mentioned that you talk about contaminants in groundwater and things like that. You know, I'm in London, for instance, and right between Huron and Lake Erie, we want to go swimming all the time in the summer, and water contamination is something that we have to deal with all the time. And how is your research sort of helping identify, you know, what we're dealing with every summer?
Well, so one of the projects, I've been here at Nipissing University just for the last 2 years, and the Canada Research Program was part of what brought me back to Canada from the United States. So over that time, we started working with the North Bay Mattawa Conservation Authority, which is our local conservation authority here in North Bay. And so you would have, of course, equivalents all across Southern Ontario that might be dealing with these issues. And they have a local watershed, for instance, that's interested in phosphorus levels and occurrence of blue-green algae. And so we are developing a project that looks at the hydrology of that watershed. It's fairly large, 250 square kilometers. It headwaters kind of close to Algonquin Park in terms of, you know, that classic Canadian Shield kind of terrain. But then, you know, up here in North Bay, we have these clay belts. So, your question about groundwater and surface water, we need to take the geology and the landscape into consideration. And there's some pretty big differences between Southern Ontario and Northern Ontario in that respect. So you're always going to kind of get local with respect to what is our landscape and how does groundwater and surface water kind of interact in that setting. So we're using those kind of measurements that I talked about earlier, and we're also using like the geochemistry. We're making observations, we're sampling water in the streams, in the lakes, to look at the geochemistry of that water. And there was a question about, you know, how long it takes, right, for water to move through our watersheds. That's a really big question. We refer to it as residence time of water. And so we can get at questions using geochemistry and using stable isotopes, which if you think about the water molecule itself, right, is made up of hydrogen and oxygen. And there's naturally occurring heavier and lighter oxygen, and naturally occurring heavier and lighter hydrogen. And we can use those measures of those as tracers, what we call tracers of water movement.
That's awesome. May I ask another question? You're talking about the differences in landscape. When I asked the question about timing, one of the things that occurred to me as you were replying was whether, so you talked about having a very long data set as well as looking at things as short as an individual rainstorm. So in Sudbury, it's very pretty now. I just want to point out, it's a very pretty place now. But I mean, it's known internationally for having been just this ecological devastation site, right? And we lost somewhere in the neighborhood of a meter of topsoil in many places. And given that we were just glaciated, a meter of topsoil is a lot of topsoil. So I would expect that that kind of human impact would change the time course of some of these events that you're following. So can you look at some of the longer term data sets and look to see how we are impacting things like residence time in a watershed?
Well, so that's a really good question. I mean, I think in order to, how are we affecting residence time of a watershed? I think in our science, if you think about, I know the hydrologists I work with or the international folks that I follow through their publications, quantifying residence time, an average residence time, because you can imagine that some water might move very quickly, some of it might move very slowly through a watershed. We have to talk about an average residence time with some kind of distribution. How do we get a handle on that? That's this huge issue in hydrology that people are struggling with or grappling with internationally. Then how are we actually changing that? Because I agree, in Sudbury, as you say, if you've lost that overburden, you've lost the ability to infiltrate water, so you might end up with a system where you don't have that soil to store water. It's just going to flash right out in that respect because there's no, you've lost a lot of that potential storage. I don't know if those, at least in the case of, if you had an experimental watershed in Sudbury 200 years ago and you'd started monitoring, that would be super ideal to be able to then march through time. I don't know if those exist. I mean, but that's a really good question. One of the things we do then is we move to models, right? Yeah. So it's another technique we use is, can we develop watershed models that mimic or essentially represent all the important processes that are important to move water through the system and to replicate maybe their chemistry as well. And then if we can do that, then we can talk about these what if scenarios. What if you changed this kind of characteristic of the watershed, or you changed climate, or you changed, or you added contamination, what would happen?
Yeah. So Colin, how do we tie this back?
Well, actually, before we tie it back, I wanted to just mention a little bit, because you actually got into the model idea. I wanted to ask, because this is such a variable field, right? In terms of doing experiments, but you're also, like you mentioned, you're tied to geology, you're tied to different soil types, you're tied to different terrain, all of that kind of complexity. I was wondering about the relationship between doing experimental and observational science outside in the field, and then how it relates to what goes on in a laboratory, and you mentioned modeling, and sort of, so maybe just briefly talk about, for a high school student who doesn't know what that refers to, what would a model be, and how does the outside digging wells relate to what you would do in terms of a model that you would then work with?
Well, so yeah, I've done my fair share of both experimental work in the field and modeling behind a computer. So we often use these are computer-based models. And so we would, or at least let me talk about the computer-based models. And so these are mathematical equations that we've essentially written, or, there's a lot of off-the-shelf models now that we can then apply to our specific watershed. And so I need maybe a little bit of computer programming background, some math background, in addition to my geology or my geography or my hydrology courses, in order to kind of get comfortable with that world. Now, I want to simulate what's happening in terms of stream flow responding to a storm event or a 30-year time series of rainfall and temperature. I need that data from the field to help understand my model and to constrain the possibilities. And I'm not only these days going to use data from stream flow and maybe water table levels and the dynamics of what's happening in the field, but I might also use those stable isotope concentrations of water in the stream that are monitored at these research catchments, or the geochemistry. So the more ways I can test my model with real data from the field, Not that that isn't challenging. There's some issues related to point scale measurements and, the grid size of my model. But the more ways I can test it, the better. There's some famous academics that I've met, and one of them is particularly famous for rejecting all his models because it's not adhering to the data, right? And so, so we want to test our models. We want to see where they fail. We want to see where they're consistent with, the observations. But that might not be enough. We might need more. So as a researcher, I'm constantly going back and forth between, working with a model and working with experimental data, and you might be working with different people playing these roles as well.
Mm-hmm. So you've made a ton of connections to curriculum for students in just that last little couple of minutes of conversation, because I was sitting here and I've got my science curriculum documents in front of me, and I was flipping through them earlier today, and there's some very obvious tie-ins with things like grade 9, sustainable ecosystems in grade 9, and climate change in grade 10, and how climate change affects water and water flow and hydrology. But then you also mentioned math, you mentioned physics and chemistry a little bit, and you talked about isotopes and the geochemistry, you mentioned computer science in developing the models. So am I correct in assuming that what you do is a very interdisciplinary field and you're drawing on a whole range of different things? So if I was a student interested in this, I need to be sort of interested in a lot to be able to approach it in the way that it needs to be approached. Is that fair to say?
Well, I think you can come at it from different pathways. I mean, my pathway was very circuitous in that I did an engineering degree, I did engineering physics, and then I kind of shifted over into the earth sciences. And when I came into the earth sciences, I had this wonderful math and physics background, and I could do some computing. And then I brought those tools with me. Now, I'm not saying you have to do all of that. You don't have to do a degree before you move over. But my father was a geologist at Laurentian, actually. And so, I made that, and I saw him doing field work, and I said, I really want to use these tools to study natural systems, and I got really jazzed about water movement. And so, I don't think students have to identify, exactly where they want to go, but these tools, emphasizing the fact that that quantitative toolbox, even if you're going into, a science that they don't necessarily link to math or computer science, guess what? Those tools are really, really powerful in those fields, and you can have great fun with them.
Yeah, that's an awesome point. I'm also from the U.S. and moved up here, and one of the things that's kept me here is the CRC. So that program was designed to either bring in Americans, keep Americans, or keep the Canadians here. So it seems to be working. One of the things I think the American higher education system does a little better than some in Canada is promoting a breadth of education. And a lot of research is moving into more interdisciplinary, Colin, as you said. And
yeah, sure.
There are very few researchers who work in isolation. Most of us collaborate with this person, that person, this person. But the stronger the foundations that you can put together. I mean, you can't stress enough how important a good English background is to being a scientist. And I just rejected a paper yesterday for review because I couldn't read it. And it was written in such non-standard English that there was no way to interpret it. So, if you want to be a hydrologist, you also really have to understand how to communicate. And a large part of that is how do you write a complete sentence that other people can understand. So it's amazing how much a science background requires, and honestly it's not science, how much a career in anything is going to require some kind of foundation in the basics of English, math, and the other ones that I've already forgotten. So we can't stress that enough. I wish I had more math, and I have a fair amount of math, and I would be a so much better scientist if I had more math. So I really appreciate April you bringing that point up.
Great. Does anybody have one last question before we head out?
I have lots, but we'll save them for another time.
Great.
Feel free to call anytime. It was a delight to participate.
Awesome.
Oh, good. Wonderful. Thanks very much for coming on.
Thank you so much. So a special thanks to Dr. April James and also the University of Nipissing. I'm Nicole Tate-Hill, and this was This Week in Science and Education.